बता देना एंड लगा देना. Right? So welcome to IMS GATE Academy, my dear friends. You know that we have been continuing this most expected concept series on heat transfer, and we have done 4-5 sessions as of now. We have already covered some of the important concepts of conduction, the most recent one being the lumped analysis that we discussed, right. So today we will be continuing on the same page, and continuing from the conduction only, we will be learning an important concept of heat transfer, that is fins. We will learn the concept of fins, right. So today what we will do, I will tell you the sequence of topics. In fins we will be first seeing what is the, in fact we will be deriving what is the differential equation for the fin, and then we will see some most important cases which are important from the examination point of view and from the fins perspective as well, right. So my dear friends, let us start today's topic. So this is today's topic is fins. My dear friends, in the rear downside of the bike or near the engine side, if you focus, or in the back side of the refrigerator, if you see, you will see some extended surfaces, right, in the something like this shape you would have observed, right. What are these? These are nothing but the fins. Why are they made? That we are going to see. My dear friends, see, for example, you know that Q is equal to HA delta T. What is this heat? This is the convection heat transfer. Now assume that this is a surface of any equipment. This is a surface, and over here a high temperature is being generated due to any process, be it an engine or the backside of a refrigerator. Some high temperature is being generated over here. Now when heat is being generated, it needs to get convected to the surroundings. Else what will happen? The entire area will heat up a lot, and when something heats up a lot, the material restrictions are also there, right. So we need heat to get convected in the surroundings. Very good. So there are two things. Either the H of the surrounding is very high. So if H is very high, so see, delta T, T of the surface minus T of the surroundings. So I can say that this is more or less fixed only. Fine. If H is very high, if the heat transfer coefficient of the surrounding is very high, then no need of making these fins. It will be, my heat dissipation requirement is very low, and very low means considerably low, and it is very well adjusted due to the high H of the environment. Then it is very good. I need not make any fins or something like that. But suppose that this H is very less. Very less means the ambient temperature, the normal temperature of the surrounding, and you need heat to get dissipated. For example, in the refrigerator, you need heat to get exhausted. Your H is very nominal of the surrounding. So in that case, I need to increase the heat transfer area. This is the only way by which I can increase the heat transfer rate. Why I need to increase the heat transfer rate? So that heat ultimately gets dissipated, heat generation doesn't takes place. So the only way is increasing the heat transfer area, and that is why we need to make fins. Fins is required. So what are fins? Fins are the extended surfaces. It is the purpose of fins is to increase the heat transfer area, and that is why we increase the heat transfer area. Fine. So this is the concept. Now we will be seeing differential equation of a fin. differential equation of a fin. So just assume that this is the surface that we are talking about, and over here you can see that, let's say you can take a circular fin also, that is not the case, but let us assume that I have attached a rectangular fin, so because rectangular fins are generally easy to analyze. The length of the fin is L, the width is W, and the thickness is T. T naught is the temperature at the base of the fin, of the material base. This is the T naught, and let's say the ambient is having a heat transfer coefficient of H. Obviously your surface is very hot. This means from here what is happening? From here, from every side heat is coming and it is getting conducted through this fin. It is getting conducted through this fin, and ultimately from the surface of the fin convection is taking place. From all the surfaces convection is taking place. So heat is getting conducted, and at the same time it is getting convected to the outside environment, and this is the only way by which we can balance we can dissipate whatever heat is coming from this base to the outside environment. Else if we don't dissipate, it will lead to heat generation, it will lead to increase in temperature of the material, it will lead to material failure, and etc. See what happens. For example, I will try to show you one thing. For example, if the base temperature is, let's say, 80 degrees centigrade, so when the heat is getting conducted and convected, so the temperature across the length, it decreases. Okay, when it decreases, so for example from 80 it has started, so 60, 50, and by the end of the length of the fin, it is possible that it has reached a temperature of, let's say, close to ambient temperature. Why temperature decreases? Because heat is getting convected every time of its across the length of the fin. So now my question is, or anyone's question can be, sir, I want to know the temperature at a particular length of the fin. Number one. Number two, sir, I know that temperature is decreasing. Matlab by common sense I know that temperature is decreasing, but what is the exact relation by which I can say that it is decreasing? Is it decreasing logarithmically? Is it decreasing exponentially? Is it decreasing parabolically? All these things I want to know. And second, I want to know what is the heat actually getting dissipated through the fin surface. All these things I know. I already told you in the beginning of conduction that majorly in conduction we are interested to know about the temperature profile. Number one, what is the heat transfer? Number two, what is the nature of heat decrease or increase? All these things we are interested to know, right? So the same thing we are going to do in fin as well. So what I will do, so let me erase some this. Okay. So let's say I will see when something changes across the length. For example, temperature is changing across the length. So I will need to analyze a small portion of the fin, and I will apply the energy conservation criteria over there, and based on that whatever comes we will check. So for example, I am trying to analyze this portion of the fin. I am trying to analyze this portion of the fin. So what is actually happening here? At this surface, now assume that this is at a distance of x, this is at a distance, this face is at a distance of x from the base. So I am assuming this thickness has to be dx, so this face automatically will be at x plus dx. So at this part, if qx at this phase, the first phase, if qx is getting conducted, so over here it will be qx plus dx. Okay. So let me bring this material over here and let us try to see in detail what is actually happening. So there is the face. At this face, qx is coming. So from this face, qx plus dx is leaving. Why? Because this is dx. And from the top surface, now top surface and bottom surface also, heat is getting convected. And from this side surface and from this side surface, heat is getting convected. So if I ask you that from how many faces heat is getting convected, there are 4 faces heat is getting convected, and these 2 surfaces heat is getting conducted, right? Okay. So I will have to apply energy conservation criteria. So energy is entering at this phase, and what is going out? So I have to apply equal to sign. What is going out? It is x plus dx plus the total energy convected is going out, the total energy convected from the 4 surfaces. Now I have told you one thing, that using Taylor's expansion, in the first class only I have discussed that we can write this thing as qx plus d by dx of q of x into dx using Taylor's expansion. Now don't cancel this dx and this dx. Okay. So let me go to the next page. So qx is equal to, in place of qx plus dx, okay, I am writing once again, this is the thing that I have written, plus q of convected. So this is q of x. Now using Taylor series, I can write this as to be qx plus d by dx of qx into dx, and still I have to find the value of the total convected. So obviously I can cancel out this qx and this qx. So 2 things I need to find out. First, what is this value qx, and second, what is this q convection total. So from here you can see that conduction is taking place through this cross sectional area, and you know that it is normal to the cross section. So if I assume the cross section area to be AC, so I can write using Fourier's law of conduction minus Ka dt by dx. What about the convection? Convection is taking place from 4 surfaces, from 4 faces I should say. The width is W and the thickness is T. So what is the area of convection? Because then I will be applying Newton's law of cooling. So area is equal to this dx into T into dx, and that is front and back. So 2 times plus Now the top surface and the bottom surface. So W into dx, W into dx and into twice. So I can write 2 T plus W into dx. Now see, this is T and this is W. So I can say that for the cross section, this is the perimeter itself. For the cross section, this term is the perimeter. So I can write perimeter of the cross section into dx. So for A, I can write P dx. Okay. So conduction already I have told you. So this thing I am writing. This is d by dx, and for qx I can write minus k AC, AC is the cross sectional area, dt by dx plus what is q convection? So already I have told you, first you will write H and A. So in place of A, we have discussed that I can write area as P dx. Area as I can write P dx, and the temperature I have to assume that the temperature for this particular strip, rectangular strip, I have to assume as T. Now this thickness is so small that temperature is not varying. The only purpose of taking a small strip over here is that it is so small that temperature can be assumed to be constant of the strip, but outside temperature is T infinite, ambient. So what is the temperature difference? T minus T infinite. T minus T infinite is equal to 0. Okay. Okay. So this I can take it to that side. So this is d by dx k AC dt by dx. This is a minus sign, I am taking it to that side, and that is equal to H P dx T minus T infinity. Yes, I have missed this dx, don't worry, I can write here. I have missed this dx, so I am writing this dx over here. Now this dx and this dx gets cancelled. Now I will assume that K is independent of temperature. K of the material remains constant, K is independent of temperature or distance, and AC also I am assuming to be constant. I am assuming that the cross sectional area remains constant. Cross sectional area remains constant, and K is also independent of temperature. So KAC I am taking it out, and then I can write this as d2T by dx square is equal to HP, and this is T minus T infinite, right? So what we have got till now? I have got d2T by dx square, this is HP by KAC T minus T infinite. Now I will, for mathematical analysis, mathematical simplicity, I will take an assumption. What is that assumption? I will assume that or I should write it over here, let T minus T infinite be theta. For mathematical simplicity, I am going to assume something that is T minus T infinite, that is temperature at any distance of the fin, and the difference with the surrounding, the difference is theta. So if I apply D, that is the differential, I have to apply D of theta. This I can write as D of T minus D of T infinite is equal to D of theta. Now D of T infinite will be 0. Why? Because T infinite is constant. And then I can write dt is equal to d theta. and therefore I can also write d2t by dx square is equal to d2 theta by dx square, right. So using these substitutions, in place of this I can write d2 theta by dx square is equal to hp by KAC, and this I have assumed theta. Again, now this term is there, HP by KAC, this will appear again and again. So why always say HP by KAC? It's better that we assume this thing to be m square. This thing I am assuming to be m square. So d2 theta by dx square minus m square theta is equal to 0. Again, why I am assuming m square? It is also for mathematical simplicity. You can assume m also, that is not the problem, but just to get better answers, we are writing m square. So finally, this is the differential equation of the fin. This is the differential equation of the fin, and whatever analysis I do, it will start from here only. I repeat, this is the differential equation of the fin, and whatever analysis that we do, whatever heat equation we found, whatever temperature profile we find out, it will be starting from this equation only, right. So why I have derived this? Because so that you get to know all the assumptions that is there, and what are the main assumptions. One of the most important assumptions is that the cross sectional area I have assumed to be constant, number one, and then K is independent of temperature, that is also there. H is constant, H that is the heat transfer coefficient is constant. Material is homogeneous isotropic, that is understood by default. So all these things I have assumed, for my derivation of the differential equation of the fin. So let us again start our derivation or analysis from this equation. Okay. So what is the differential equation of the fin? That is d2 theta by dx square minus m square theta is equal to 0. Now this is the differential equation of the second order, and in engineering mathematics you have studied or you will study that if I have to find the roots are real and distinct. So I can write from differential equation C1. So first of all, let me tell you what are the roots. So roots will be plus and minus m. Roots will be plus and minus m. Plus and minus m. So theta will be, you are solving for theta C1 e to the power m1 x plus C2 e to the power minus m x. So this is the, so what we have found out? We have found out theta versus x profile. Theta versus x profile. Theta variation with respect to x. Now what is theta? Theta is the temperature difference at any position. Temperature variation with respect to x. Theta versus x. Theta versus x. Theta, always remember, this is the temperature difference. This is the temperature difference at any x. At any x. Clear? Is the temperature difference at any x. So obviously you can see that if you have to find the exact theta, you will need two boundary conditions because two constants are there, C1 and C2. So all these things are fine. ठीक है, what is m by the way? If I ask you what is m, so m is root over hp by kac. m is hp by kac, hp by kac. ठीक है. So there is the difference. One more thing. This theta can also be written as a cos hyperbolic mx plus b sin hyperbolic mx. These and this are same, no differences are there. No differences are there. This equation and this equation are same, no differences are there. Why? Because you know that cos hyperbolic mx can be expressed in terms of exponential functions. I repeat, this function and this function are same. Why? Because you know that cos hyperbolic function and sin hyperbolic function can be expressed in the term of exponential functions. Now, this is one relation and this is one relation. In place of cos hmx and sin hmx, if you substitute this, you will probably come over here, right? So link also I have told you how to get. So why I have told you these two? Because sometime in one case I will be using this equation to start with, and in another case I will be starting with this, right? So why? Because both are same only. We will arrive at both the, we will arrive at the same equation, or there is no particular no difference if I use this or this, it will give me the same result. Okay. So till now I will tell you what we have discussed. Till now in this half an hour time we have discussed the differential equation of the fin. What are the assumptions associated with it? We need two boundary condition every time. And I can say that one boundary condition will be same in all the cases. What is that boundary condition? The boundary condition is that at the base of the fin, the temperature is T0. One boundary condition is always fixed. What is that fixed boundary condition? At the temperature, that means at x equal to 0, the temperature is T0. This is always fixed. Okay. So it is for the second boundary condition that we take different cases. That is why you study majorly 3 different cases in fins. I repeat, there are two differential in the differential equation. There are two constants C1 and C2. I need two equations to solve them. One equation is common in all the cases, and that is at x equal to 0, the temperature is T0. Now it is for the second boundary condition that we make 3 different cases. In 3 different cases, it is all about the second boundary condition that will keep on changing. The first one will remain the same, right? So let us discuss the first case, and that is the infinitely long fin. Case 1. Case 1 is infinitely long fin. Now, what do you mean by infinitely long fin? I will tell you. Just a minute. Yes. So, for example, assume that this is the fin. Assume that this is the fin. Okay. So, at the base, let us say the temperature is 80 degrees centigrade. Now, at some distance from the base, it is, let us say, 60 degrees centigrade. At some distance, it is 40 degrees centigrade. Now, if you keep on, that means if it is a very long fin, so ultimately what will happen, assume that the ambient temperature is somewhat 25 degrees centigrade. So at the end of the fin, at the end of towards its length, the temperature will approach T infinite, that is 25 degrees centigrade. 60, 40, 30, 35, and ultimately if it is a very long fin, so the temperature will assume the ambient temperature itself. So if I ask you what is the temperature difference at L equal to, that means infinite, that is very long, you will say 0. If I ask you what is the temperature difference at the end of the fin, you will say, sir, it is 0. Why? Because it is ultimately approaching the ambient temperature. So you know what is the condition to begin with. The condition is theta is equal to C1 e to the power m of x plus C2 e to the power minus mx. So the first boundary condition already I have told you, which is the common one, that is at x equal to 0, what is the temperature? It is T naught. But we are not actually finding the relation with temperature. We are actually interested in theta. Remember, if you remember, we are actually writing theta, not temperature. So theta will be T naught minus T infinite, and I can assume that it is theta naught. Very good, sir. Similar, the second boundary condition, that is at x equal to L, and you have assumed L to be very long. Very long, that means I can write L to be infinite. Obviously, any length cannot be infinite. It is only for the mathematical purpose that we are writing L as infinite. The temperature is nothing but T infinite ambient, and so theta will be T infinite minus T infinite, that is 0. So using these two boundary conditions, I will be deriving the temperature profile. So now I am using the second boundary condition in this. So that means the second one. So theta equal to 0 at C1 e to the power x as infinite plus C2 e to the power minus m infinite. So this minus m infinite, what will happen? 0. C1 e to the power m infinite, that means C1 into infinite, and this thing will, when it come into the denominator, it will be 0. So this is vanishing, this term vanish. C1 into infinite, left hand side is 0, so that means C1 must be 0. Then only the LHS and RHS will be satisfied. So C1 will be 0. Now don't apply the concept of limit over here. You will say that, sir, 0 into infinite is indeterminate form. So no, that concept is not there. We are talking about the absolute values. And second thing, infinite doesn't means very, very long. It means a very large number. That's it. So anything multiplied by 0 ultimately comes out to be 0. So C1 is 0. So what is theta now? Theta is equal to, C1 is 0. So C2 e to the power minus mx. So theta is equal to C2 e to the power minus mx. Okay. The first boundary condition is at x equal to 0, theta is equal to theta naught. So theta is equal to theta naught is equal to C2 e to the power minus 0, it is 1, e to the power minus 0 comes in denominator 1. So C2 is equal to theta naught. So I have got both the values of the constant, therefore theta is equal to theta naught e to the power minus mx, or you can also write theta by theta naught. So same thing only. So you can see theta versus x profile as what type. In the beginning only I told you that we are interested in knowing the profile of theta and x. Theta naught is a constant value, m is a constant. So theta and x variation is what? Negative exponential. So variation is negative exponential. Negative exponential. So what exactly is negative exponential? The temperature decrease from the base of the fin till the end of the fin. You know that temperature was decreasing, but how it is decreasing? Negatively exponential decrease is there. I repeat again, this is the fin. This is the fin. I am only showing the cross sectional. So you know that here temperature is around 80 degrees centigrade, and you know that temperature is here around some 30 degrees centigrade. You know temperature is decreasing, but how it is decreasing? It is decreasing negatively exponential. This is the meaning of this derivation. Okay, this is done. Now second, we are interested to know that what is the steady state heat transfer at the base. See, we are assuming no case of heat generation, no heat generation is there, and also we are assuming that it is a case of steady state heat transfer. Steady state heat transfer means what? That at any phase, whatever heat is coming, it is leaving that phase. That's why temperature of a particular phase is maintained constant. I repeat again. For example, if I say that this phase is having a temperature, obviously phase means this is the phase that I am talking about. Similarly, this will be the phase. This will be the phase here. Similarly, this will be the phase. I told you I am only showing the cross sectional. So if the phase is 80 degrees centigrade, if this is 60 degrees centigrade, if this is 40 degrees centigrade, and I am saying that it is a steady state heat, steady state condition that we are discussing. So what is the significance of this? Significance is whatever heat is coming in a particular surface phase, it is leaving, then only the temperature will be maintained constant. If something is coming, if the same thing is leaving, if I give you 10,000 and you give 10,000 to your friend, what you are left with 0. That is the thing. If 40 watt of heat is coming, 40 watt is leaving, that's why we refer this to be a steady state condition, and that's why the temperature is remaining to be constant. Okay, this is done. Now at every, now what is the process that is going on? The process that is going on at any section is heat is getting conducted and heat is also getting convected. Heat is conducted and heat is getting convected also. So we are interested to know that what is the total heat conducted at the base of the fin, that is at the beginning. What is the heat that is coming out? That heat we are interested in knowing. I repeat again, at any section if you analyze, heat is getting conducted across the length of the fin and heat is getting convected also. then only I need to dissipate the heat na. So that's why we can say that the temperature is also decreasing. Very good. This was our purpose. So what is the total heat which is coming from the base, and that is the heat total that is getting dissipated. So that heat I am interested to know. That means I want to know heat at x equal to 0, and what is the heat that is getting dissipated or convected. So this can be found out by applying Fourier's law at x equal to 0. So that is nothing but minus k AC dt by dx, and you know that dt is equal to d theta. dt is equal to d theta, that we have discussed earlier only. So minus k AC, I can write this as d theta by dx. Very easy, right? Why I am writing AC? Because cross sectional area, and I have treated this to be constant. Okay. So d theta by dx, and that too at x equal to 0. That too at x equal to 0. So here I am writing. Here I am writing. No, don't worry. Theta is equal to theta naught e to the power minus mx. I want to know what is d theta by dx at x equal to 0. So theta naught e to the power minus mx into minus m theta naught e to the power minus mx, and then if you substitute x equal to 0, at x equal to 0, what is the heat? What is the d theta by dx? So d theta by dx at x equal to 0. So this will become 1. E to the power minus 0, take it to the denominator, it will be 1. So you are left with minus m theta naught. Minus m theta naught you will be left with. So if I write it over here, it will be minus k a minus m theta naught. So let us take it to the next page. Q is equal to minus k AC and minus m theta naught is equal to k AC m theta naught. Now what is m? M is root over HP by KAC into theta naught. So I think we can simplify this, and we will be left with HP KAC and theta naught. What is theta naught? What is theta naught? Where theta naught is nothing but temperature difference at the base. So T naught minus T infinite. Now when I say that it is a case of steady state heat transfer. When I say that it is a case of steady state heat transfer, that means it should be a constant value. It should be a constant value. So see, H is constant, perimeter of the cross section is constant, thermal conductivity of the material is constant, cross sectional area is also constant, and theta naught is also constant. So all in all, I can say that it is a constant value, and that's why I can say that it is a case of steady state heat transfer, the constant value. Okay. So right now we have two equations from the case of infinitely long fin, and that is, one equation is showing the temperature profile, which is the case of negative exponential, and second is the steady state heat transfer at the base, and that is root HP KAC into theta naught, right? So two equations you have to memorize, and that we have discussed. Now we have case 2 with us, and case 2 is case of insulated fin tip, fin with insulated tip. Fin with insulated tip. Fin with insulated tip. Okay, just a minute. Okay. So let us try and understand what is this case actually. So this is a surface, and over here a fin is attached. Now, what is the meaning of insulated fin tip? That we should understand first. When heat is getting conducted from the base, when heat is getting conducted from the base, it is convected from the surface of the fin. Now, if you see what are the major areas of convection, it is the top surface, it is the bottom surface, it is the side surface. This from here also heat is getting convected. It is this side surface from where heat is getting convected, right? Base it is conducting, from here it is not convecting. So majorly I can say that 4 faces are there from which heat is convecting. Now if you see this face, it is actually very less area, it is having a very less cross sectional area as compared to, or I can say the surface area is very less as compared to these 4 cases. So for very safely I can say that, or very safely I can ignore that whatever heat is getting convected from here, that I can very easily ignore. For example, if total 100 units of heat is to be convected, so from these 4 surfaces I can say 95 units are getting convected, and from here I can say only 5 units or less is convected. That I can, why I am saying this, in reality heat is definitely getting convected, but for the mathematical purpose, for getting the second boundary condition, we are assuming this boundary, we are assuming this case. ठीक है? For the purpose of second boundary condition, we are assuming this scenario. So what exactly I am saying? I am saying that from here heat convected is 0. So I can also say heat conducted is equal to heat convected is equal to 0 from this phase. So what is heat convected? Minus Ka. So dt by dx, so better I am writing d theta by dx is equal to 0. K and A cannot be 0, so therefore d theta by dx is 0, where at x equal to L, at x equal to L, d theta by d. So this is itself is giving me one boundary condition, one boundary condition, and then you will ask, sir, where is the first boundary condition? So already I have told that one common boundary condition is there, and that is at x equal to 0, theta equal to theta naught. So using those two boundary conditions, we will be getting a different temperature profile. Okay. So as I said, I will be using this time the hyperbolic functions to get the answer. Why? This is purely mathematical simplicity. So this time I am assuming this function, and you know that both functions are same only, whether you go by that, whether you go by this, it will be same only. Just for mathematical deriving good expressions, easier expressions, we are changing the functions. So you know that the first boundary condition at x equal to 0, t is equal to t naught, and so therefore theta is equal to theta naught. So when you substitute 0, cos 0 1, sin 0 0, so you are getting theta naught is equal to a. So theta is equal to theta naught cos hyperbolic I need to find b value. Okay. So second boundary condition is d theta by dx equal to 0 at x equal to L. So d theta by dx, now find out. So it will be m theta naught, now sin hyperbolic mx. Now don't write minus, in case of hyperbolic it is cos ka sin, sin ka cos, plus mb minus mx, and if you find out at x equal to L, at x equal to L if you write, it will be 0. So I can write, acha, m and m gets cancelled. So theta naught sin hyperbolic ml plus b cos hyperbolic ml equal to 0. So b I can write minus theta naught sin h ml divided by cos h ml. Obviously you can write tan h ml also, that is not the case. But as of now I have got what is the value of b, and I am writing theta. So theta is equal to theta naught a cos hyperbolic mx minus, now what is b? Theta naught sin h ml by cos h ml into sin h mx. Okay. So we have got both the C1, C2, A and B value we have got, very good. So now I can focus on simplifying this. So this is theta naught cos h mx cos h ml. Theta naught you can take common, that is not the issue, minus sin h ml and in the denominator it is cos h ml. Now this expression in the numerator that you are seeing, it is cos hyperbolic m L minus x I can write divided by cos hyperbolic ml. So this is the temperature profile that we are getting for in the second case. Now, I will be asking that, sir, what is the nature? Obviously, when I can write cos in terms of exponential function, so it is also exponential only. That is not the thing, only the values will be different in this case, but the nature will be same. Why? Because I can express it in the form of exponential. This one case. Now, do not forget, we have to find the value of heat transfer also. We have to find the value of steady state heat transfer, and that is nothing but minus K AC d theta dx at x equal to 0. Okay. So, first K and AC are fine, but we have to find d theta by dx. Okay. So, d theta by dx, so this thing is constant, this thing is constant, only this is the variable. So, d theta by dx is theta naught by cos h ml. Now, cos का sign h ml minus mx, and chain rule say it will be minus m. By chain rule it will be minus m. So, it will be minus m theta naught. Now, when you substitute x equal to 0 over here, at x equal to 0, when you substitute x equal to 0, this will be gone, this will be gone. So, you will be left with sin h ml cos h ml. Now this I can write as minus m theta naught tan h ml, tan h ml. So, this is all at x equal to 0, do not forget x equal to 0. So, now we can very neatly substitute over here, minus K AC. So, we are getting minus m theta naught tan h and ml. So, it is K AC m theta naught tan h ml. M you know, m we know as root over HP by KAC. So, Q will be KAC root over HP KAC now this I can reduce it. So, this is the steady state heat transfer that we will get in the second case. This is the steady state heat transfer that we will get in the second case. So, we have the temperature profile over here and we have the steady state heat transfer case that we have over here. We have to memorize these two equations. So, in the first case, that is infinitely long fin, I have given you two equations. Over here you have two equations, right. And we can also derive some conclusions over here, that this case, if you see the heat transfer from the first case and if you see the heat transfer from the second case, only the extra term is that this tan h ml, hyperbolic ml. If you make this as 1, that is the tan h ml term as 1, so you will reach the infinitely long case, right. So, for a particular value of L, this value will come out to be 1, Okay, so we can draw conclusions from here that when L is some value, that means tan h ml is 1, then only we can say that this case will behave as infinitely long fin case. Okay. So, till now what we have discussed? I will just brief it once. First of all, we have discussed the differential equation of the fin. Then we have discussed the infinitely long fin case, and then we have discussed the fin with insulated tip, and now we will discuss the third and perhaps the last case. I can name it as the one of the general case, I can say. Sorry. That is the fin with convection at the tip. Fin with convection at the tip. Fin with convection at the tip. That means in the previous case, that is in the second case, sorry, yes. So, in the second case, I have assumed that purposefully I neglected the convection from the tip. And over here I am not going to assume that. Over here I will be assuming that there is convection taking place from the fin's tip. No scope of error I am keeping as of now. So, there is the tip and from here convection. That means whatever Q is conducted over here, that is the heat convected from here. So, I can say that Q conducted at x equal to L is equal to Q convected at x equal to L. What is Q conducted? Minus K AC dt by dx at x equal to L is equal to, what is the Q convection? HA. Now you have to assume that the temperature at this surface is TL. You have to assume that the temperature at this face is TL minus T infinite. So if you equate both these things, if you equate both these heat transfer, then only you will be arriving at the second boundary condition you will get. First we already have that at x equal to 0 the temperature is T naught. At x equal to 0 the temperature is T naught. This is the length of the fin and width and thickness are there. So you can do in this way, you can do in this way. And for simplicity you can do one more thing. For simplicity you can do one more thing. What you can do, I am just explaining you. For simplicity you can do one more thing that we generally study, and that is what I am going to tell you now. See, what we will do, we will use the second case over here. We will use the second case now. What was the second case? Second case was insulating the fin tip. Insulating the fin tip. Insulating the fin tip was the second case, and in the third case we are neglecting that, we are removing that. So what I will do, I will see if I have to ignore the heat convected in this. What was second case telling you? Second case was telling us that you have to ignore the heat convection from the tip. So if we have to implement that second case in this third case, so I will have to assume that from the tip there is, that means from this surface there is no heat getting convected. So what I will do, I will increase the length of the fin. I will increase the length of the fin. I will increase the length of the fin by some distance. I will increase the length of the fin by some distance, and then I will insulate the tip, so that whatever heat is, I am stopping it from this face, from the other faces, those heat can get convected. I repeat again. If I have to use the case of insulated tip over here, so what I will do, I will increase the length of the fin, so that I will increase the length of the fin and then insulate this face, so that whatever heat I am preventing from this face, I will let it, that heat, to pass it or get convected from the other faces, so that the net heat convected remains the same. That is the concept. So earlier if the length was L, now you will have to use a corrected length. Now you will have to use the corrected length. That means some del T is must there, some amount of delta L, is there. So that is the concept of corrected length. This is known as the corrected length. So this corrected length is L plus T by 2 for rectangular fins. For rectangular fins, it is L plus T. What is T? T is the thickness. And this is equal to L plus D by 4 for case of circular fins. Obviously, D is the diameter. Only this change you will have to make, and rest all the formula will remain same. All the formula will remain same. All the cases will be of the second case only. Rest everything is same, just in place of L you have to use LC. In place of L you will have to use LC. Rest all the formula will remain same. Rest second case you can use. So my dear friends, there are three cases, three major cases from which is important from the examination point of view, from where questions are being framed, and this is all the concept and formula that you need to know as far as your GATE is concerned. So if I brief it up, we have discussed the differential equation of the fin, where I took a some dx length of the fin, and then I applied the energy conservation, and we arrived at the differential equation. So I told you three cases are possible. From there, the first one was case with infinitely long fin. We arrived at two equations. Second one was case with fin with insulated tip. We arrived at two equations, and this is the most general case where I am letting convection happen, and two equations I can say, but here you have to learn only the corrected length formula. Rest you can use the second case formula over here. So these are the concepts till now that we have discussed. Okay. Now let us discuss performance of the fin. Performance of fin. Performance of the fin में the first one is fin efficiency. The first one is fin efficiency. Now what is efficiency? Efficiency is a quantity which is always less than 1. So efficiency formula is Q actual by Q maximum. Now Q actual you already know. Q actual you already know that we have found out till now. We need to know what is Q maximum. Now let us see what is Q maximum that we need to know. See, when will Q be maximum? That is the important thing. More than the formula, you need to understand that when will Q be maximum. The temperature at the base is, let's say, 80 degrees centigrade. Let's say 80 degrees centigrade. Now, in reality, what happens when you come across the length of the fin? The temperature is, let's say, 60 degree over here. Then it is 40 degrees centigrade. Then it is 30 degrees centigrade. That means when you come across the length of the fin, the temperature decreases. The temperature decreases. So, if I ask you, can I say that when the temperature decreases, the Q convection from the surface also decreases, as Q convection is proportional to delta T? So, as we move across the length, the delta T decreases. That is why Q convection also decreases. That means the Q convection that was taking place at the starting of the fin, the magnitude decreases, and when that magnitude decreases, somehow we feel bad. Why we feel bad? Because initially more Q was getting dissipated, and when we move across the length, less Q is getting dissipated. Ideally, what we want that as much as Q gets dissipated. More Q dissipation is what we desire. So, now imagine a situation. Now imagine a situation where where throughout the fin I am maintaining 80 degrees centigrade. Throughout the fin I am maintaining 80, 80, 80, 80, 80. So that what is the Q? Q is H A delta T. A I can write as, if this is the length of the fin, I can write A as perimeter of the cross section into length, and into delta T. Delta T means T naught minus T infinite. T naught minus T infinite. Or I can write H into PL theta naught. So, this is my Q maximum. This is my Q maximum. This is my Q maximum. HPL delta T. See, when the surface of the fin is maintained at every face is at 80 degrees centigrade, then from every part the heat convection will be maximum, and this is good for us, right? So, what is efficiency of the fin? It is Q actual by Q maximum. So, if I take the first case, that is case with infinitely long fin, infinitely long fin. So, efficiency will be, what is Q actual for that case? Root over HP KAC theta naught. And what is Q maximum that we derived? H P into L and theta naught. So, this gets cancelled and we are left with this entire thing is M, this root thing is 1 by M, so we are left with 1 by ml. Similarly, if I use the second one, that is fin with insulated tip, fin with insulated tip. Fin with insulated tip. So you know that only a term of tan HML is there in the cube actual. In the cube actual, only an extra term of tan hyperbolic ML is there. So if you use the same one, I will simply get an extra term of tan HML in the numerator, and rest is all same. So this is the efficiency equation for insulated tip. And this is for infinitely long tip. And obviously for the third case, it is, you know, only L will be replaced by LC. That is it. Okay. That's it. Okay. The second and the last parameter that we have to discuss is fin's effectiveness. Fin effectiveness. Fin effectiveness. Effectiveness is epsilon. Fin effectiveness is when you didn't have fin. When you didn't have fin, then some heat was anyway getting dissipated. But when you had some fin, the amount of heat dissipation increased. When fin was not there, is the video clear? Is the video clear? So sorry for the technical error. Okay, question session कब होगा? Yes, it will be soon. Just stay tuned. It will be soon. At first, we are dealing with the concept series. After some concepts we will learn, then only we will deal with the question series. And anyway, extra expected questions, good level question sessions are already being going on, right? So question series is also getting conducted, and this is the concept series. Everything is getting side by side. Okay, please follow. So what is fin effectiveness? Fin effectiveness is, now I was talking about the concept that when you don't have any fin, anyway heat is getting convected from the surface. But when you attach a fin, definitely a high quantity of heat is getting convected. That means definitely there is benefit from attachment of fin. So obviously there is benefit. That means initially if 50 watt of fin was getting convected, now after fin some more than 50 will be convected. That means at least 60-70. So there is this ratio is known as effectiveness. So what is effectiveness? The effectiveness is Q with fin divided by Q without fin. Q with fin and Q without fin. So Q with fin, you already know the Q, the heat transfer that we have discussed are the Q with fin. What is Q without fin? We will try to understand. For example, this is the fin attached. This is the fin attached to that surface. Now suppose that this fin was not there, so this is the temperature of the base, and when now fin is not there. Now fin is not there, so what will be Q without fin? When fin is not there, no fin, so only heat will be convected from this portion. So it will be H, area of the base, and T naught minus T infinite. HAB, the area of the base, theta naught. Right? So when I apply in this formula, what is effectiveness? It is Q with fin Q without fin. Now let us assume the first case, that is infinitely long fin. Infinitely long fin. So what is effectiveness? What is Q with fin? Root over HP KAC theta naught. And what is Q without fin? HAB, and that is theta naught. Now AC and AB are same only. AC and AB will be same only, that is not the issue. So effectiveness will be, I can do some simplification. I am simply writing A. I am simply writing A. Don't get confused by AC and AB. AC was the cross-sectional area that I assumed. AB is the base area, and they are same in this case. They are totally same. So simply I am writing AC, and theta naught is getting cancelled. So this is the expression for effectiveness. What do we learn over here? What do we learn over here? What do we see over here? That lower H, effectiveness will be higher for low H. That means we will install fin in those conditions where H is low. Where H is high, no use of putting extra cost for installation of fin. This fin that you are installing, you have to input some extra cost. That cost you can save when H is already high. Are you getting or not? So we will install fin in only those cases or only those places where the heat transfer coefficient is low. Number one. Number two, this effectiveness is increasing or more for P by AC if this is high. P by AC, I can say it is depending on the size of the pin. Perimeter by area, I can say that it is referring to some thinness, the size of the fin. So generally, thin fins are preferred. Thins and closely spaced fins are preferred. So from this I can conclude what? Thin and closely spaced fins are preferred. Right? So this is all in fins. Whatever theory is required for question solving, all we have discussed in this session, right? So tomorrow we will be meeting with some other topic. So I hope you have enjoyed the session. For any doubt, you can leave the comment in the chat box. I will reply it personally, right? So revise well, study well, see you soon. Good night.